After watching this video lecture, students are going to be able to calculate gas stoichiometry problems at non-STP and STP conditions. So gas stoichiometry problems are going to be very similar to the previous stoichiometry problems that we've done. Basically, you're going to need a balanced equation. You're going to need to put your given into moles, and you're going to utilize a mole ratio. The main difference here is going to be that instead of just using the mole kingdom to convert grams to moles or molecules to moles, you're now going to have access to the ability to convert between volume and moles using the PV equals nRT equation. So really all the steps are going to be exactly the same as what we've done in the previous stoichiometry lessons, but now we have an additional means to being able to convert into moles. The other thing that we need to consider is the conditions at which we are calculating our problems. So non-STP conditions, so remember STP, standard temperature and pressure, is 1 atm and 0 degrees C. At conditions that are non-STP, you're going to have to use PV equals nRT if you're wanting to convert between moles and liters. If you are in STP conditions, you can use a shortcut, which has been provided here, and we'll talk about that here in a couple of our practice problems. Okay, so the problem that we have here asks how many grams of Al2O3 are formed from 15.0 liters of O2 at 97.3 kPa and 21 degrees C. Okay, so what I first want us to do is to look at this problem from the perspective of what we're given and what we're solving for. Okay, so our given here, we've been given 15.0 liters of O2. Okay, so notice our given is in liters, and what we are trying to solve for is going to be grams of Al2O3. Okay, and so guys, again, I want you to notice, just like in previous stoichiometry problems, your given and your solve for are in two different forms. It's two different substances. So we know that we are going to have the need for a mole ratio, okay, between our given and our solve for. So of course, that's going to require a balanced equation and all of the steps that come after. So as with all of our problems, guys, we're going to have a given and a solve for. Obviously, this problem gives you more values than what some of our previous stoichiometry problems are providing, but I need you to notice that, you know, with your liters of O2, you've been told that you have a specific quantity of a specific substance, and you're solving for a specific quantity of a different substance. Okay, so now that we've kind of gotten that out of the way, let's go ahead and do the things we need to do. We know this is stoichiometry, so we know we need a balanced equation. Okay, so we're going to go ahead and balance our equation here. Now that we have a balanced equation, we're going to go ahead and get our mole ratio as well. So now that we have all of our pieces for the stoichiometry problem, we then need to take our given and convert it into the language of the equation, which is moles. We've been given 15.0 liters of our gas, so we know that we're going to have to utilize the ideal gas law in order to go and take our liters or our volume into moles. So again, we're going to start out by writing out all of our variables for our ideal gas law. We see that we're solving for N. Okay, so if we take our ideal gas law and manipulate the equation, N is going to be equal to PV over RT. Okay, now before we plug in those values, of course, we need to make sure that they all match the ideal gas law, which they obviously don't. So we're going to go ahead and make those conversions now. So now that we made all the appropriate conversions, we can go ahead and plug in our values. Okay, so we're going to plug in our pressure, which is 0.627 atm times our volume, which we were given, okay, all over our ideal gas constant times our temperature. Okay, and we plug all these values into our calculator, and that's going to go ahead and give us 0.5964, okay, moles. Because our ATM and ATM cancel, liters and liters cancel, Kelvin and Kelvin cancel, so moles are left over. Okay, and this is going to be moles of O2, and it looks like we're going to have 3 significant digits. Okay, so now we have our number of moles of O2. Okay, so we have converted our liters of O2 into moles of O2 And now we can go ahead and utilize our mole ratio to get into the substance that we are trying to solve for. So let's go ahead and set that up. So now that we've taken our number of moles of O2 and utilized our mole ratio here, if we were to stop our calculation right now, we would be in moles of Al2O3. But because we don't want to be in moles of Al2O3, we want to be in grams, we're going to take an additional step and utilize the mole kingdom and subsequently the molar mass of the Al2O3 in order to convert into grams of Al2O3. So we're going to put our molar mass of Al2O3 into the calculation here, the dimensional analysis problem here. Okay, and then we're going to plug all of this into the calculator and get our final answer. And that's going to go ahead and give us 40.539, okay, to 36 40.5, okay, moles of O2, moles of O2, moles of aluminum oxide, grams of aluminum oxide is what's left over. Okay, and this is going to be our final answer for this stoichiometry problem. So guys, obviously this seems very involved, but if you take a step back and just look at the steps you've taken, the only thing that's different here than the other stoichiometry problems is that because my given was in liters, I had to take the additional step of using the ideal gas law in these problems. Otherwise, the process is exactly the same. Another note I want to point out for you guys is that in this particular problem, there was no mention of aluminum. Okay, so we assumed that this problem was indicating that the aluminum was in excess. If you were given a quantity of aluminum, you would need to utilize this in the same way that you would a limiting reactant problem and then go from there. So just keep that in the back burner. We'll come and talk about that later on. So now that we've looked at gas stoichiometry problems at non-STP conditions, I want to actually take some time to look at the STP condition problems. Okay, so a couple of things I do want to note before we go into the STP conditions is that the non-STP conditions can be utilized for any type of gas stoichiometry problem. You can always revert back to using the PV equals nRT. The shortcut that you're about to be shown now is only valid at STP. And remember that STP, our standard temperature and pressure, is 1 atm and 0 degrees C. Okay, so please guys understand that the steps that I'm about to show you, although this problem looks very similar to what we did previously, we can only use the shortcut in these particular conditions. So keep that in your notes. Okay, so let's go ahead and let's look at this problem. Okay, again guys, our given and our solve for are exactly the same as the previous iteration that we just looked. We got 15.0 liters of O2, okay, and they want to know how many grams of Al2O3 that we're going to end up with. This is obviously a stoichiometry problem, two different substances in our given and solve for, okay. So obviously what we're going to need to do is balance our equation, get our mole ratio, okay, just like we've done in the previous example. So I'm going to go ahead and do that real quick. So we've done our balancing, we've got our mole ratio, and again guys, we need to take what we've been given and put it into the language of the equation, which is the moles. Now, because I am at STP, instead of having to go through the PV equals nRT equation, I can take a shortcut. Now, mind you, you could plug in your pressure and your temperature values using the PV equals nRT, but because we're at STP, we can use the 22.4 liters per mole conversion. Okay, and so that's going to actually kind of save us some time here. So what we're going to do here is we're going to take our given, our 15.0 liters of O2, and we're going to convert it into moles of O2. Okay, and we're going to utilize this conversion factor, as you see here. We plug this into our calculator and we get 0.6696, okay, and that's going to be our moles of O2. Now, obviously, as you can see, this is much more straightforward than using the PV equals nRT equation. However, that would have been a valid approach as well. Okay, so now we're going to take our number of moles of O2, okay, and we are going to use our mole ratio to get into our quantity of Al2O3. Okay, so we have 3 moles of O2 for for every 2 moles of Al2O3. So if we stop this problem now, we would be in moles of Al2O3, but our solve for what we're being asked to calculate obviously needs to be in grams, so we need to utilize the mole kingdom and the molar mass of our Al2O3 to get into the appropriate units. So we're going to go ahead and plug that in. Grams of Al2O3 per 1 mole of Al2O3. Okay, we're going to plug this all into our calculator. Okay, and that's going to give us 45.5, okay, or 46 as our final numerical answer. Our moles and moles of O2, moles of Al2O3, moles of Al2O3 cancel. We end up with grams of Al2O3, so our setup is correct. Okay, so 46 grams of Al2O3 is what we would expect to form under STP conditions. Okay, now guys, again, we could have done this the long way. Instead of taking this shortcut, because we're at STP, we could have plugged in our 1 atm as our pressure and our 0 degrees C as our temperature and use PV equals nRT and then the mole ratio and molar mass in the subsequent steps. But because we're at STP, we can use this shortcut. Okay, so again, guys, this shortcut is only allowed at STP. Okay, so keep this in the back of your mind. It's a great way to kind of shortcut the problems, but make sure you're only applying it at STP.